So these here are the alkali metals. Those are the alkali metals. Now, hydrogen is in the alkali metals, but it's a bit of an exception because it's not actually a metal. So we will get into the why in a moment, but what is the second family here? Remember what that's called? What is the second family? That's okay, that is the alkaline earth metals. Those are the alkaline earth metals. Do you remember what any of these families over here are called? Yes? Of course. Or what this big block of metals in the middle is called. It's okay if you don't remember from grade 9. You should have learned this. So who here did learn about the families and the different groups on the periodic table? Show of hands. Okay. So this is the transition metals in the middle. And here is a very special group of elements. These are your metalloids. You may have heard them called the staircase last year. And refresh my memory. If your elements are on this side of the staircase, are they metals or are they non-metals?
They're metal.
Yeah, right, it's kind of in the name, right? They're the metals. How about those elements on this side of the staircase?
Oxygen and liquids. What about helium, gas and liquid?
Gas and liquids. If you look on the periodic table, you're not wrong, right? The color here actually tells you the state. If it's black, it's solid, blue is liquid, red is going to be your gases at room temperature. But these here are going to be your non-metals. Okay, that distinction is very important. When we start to talk about bonding, ionic bonding, covalent bonding, you need to be able to identify if you're working with a metal or a non-metal. Your metalloids kind of share characteristics of both, right? Silicon, for example, is a great semiconductor. Metals are very conductive, non-metals are non-conductive, but silicon's kind of somewhere in between. We can add little elements to it to change its properties ever so slightly, and that's the whole premise on how transistors are built, the things that effectively power our civilization today. Now, these groups here, your boron, carbon, nitrogen group, we aren't going to learn their fancy names. I'm just going to call them the boron group, carbon group, and nitrogen group. I may call the nitrogen group the actinogens, just because I'm kind of used to saying that. But do you remember what this group is called with oxygen? What is that group called?
Halogen?
It's not the halogens, but that's a good guess. That's going to be the other group we're going to mention. You may have not have heard this yet. Oh, nice. The chalcogens. The chalcogens are this group here, your oxygen group. Then lastly, this family here is now's your time to shine.
Halogen.
Those are your halogens. And what's this group here on the end of your periodic table?
Noble gas.
Okay, good. The noble gases. The noble gases. Now, these families are really important to understand. In particular, you need to understand why they are a family. So, I mentioned this already, but some of you here have brothers and sisters, right? Would you say you're the same as your brother or sister? I'd say probably not, right? Probably not. But you do share things in common with them. Families are the exact same way. They do share characteristics in common. So, why families? Why families? How was Mendeleev able to create the periodic table? He didn't know things like the numbers of protons or electrons or neutrons. He had very rudimentary information, and he was still able to make this. He was able to accurately put the elements into their correct families. How did he do it? Exactly. he used their properties to group them together. In fact, his method was so accurate that he even predicted there should be an element in this empty space. And later on they found those elements. So his characterization of the periodic table based on these shared characteristics is very accurate, or was very accurate. Now, we're going to go into a little more detail than what Mendeleev had access to. And that is, the reactivity of families is determined by the number of valence electrons. What does that word mean, valence electrons? Yep.
Last shell?
Yeah, your outermost shell. How many electrons are in that outermost shell? So if we looked, for example, at, say, this element right here. What element is this, by the way? That's sodium. If we look at sodium, how many valence electrons does sodium have?
Two.
Sorry?
Like, one. Like in the last cell, there's one.
Yeah, there's one valence electron. Now let's look at, see if I can, perfect. Now let's look at all of the members of that family. Let's see if we can see a pattern. So if I were to draw hydrogen, it would look like this, right? Got your nucleus in the center. Got an electron there. If I were to draw lithium, it would look like this. And if I were to draw sodium, sodium would look like this. What do you notice about these elements? What do they share in common?
The donor.
Excellent. They all have one valence electron. So for those of you that did the Bohr diagrams assignment, pull that out right now, the Bohr diagrams. Tell me, what do you notice about the alkaline earth metals, that second family? Say that again? Yeah, there's two valence electrons, right? If you look at beryllium, magnesium, calcium, there is two valence electrons. How about the boron group? If you look at boron and aluminum, what do you see?
They're having three.
They have three. Carbon 4, nitrogen 5, oxygen 6, fluorine 7, and neon 8. Right? So what is an addition we can add to that definition of a family? They share a set of chemical, physical properties. What else do they share?
Their last valence electron.
They
Their last valence electron.
I understand what you're trying to say. They share the number of valence electrons, right? They have the same number of valence electrons. What Mendeleev didn't know was that is what gives those elements that shared set of characteristics. The valence electrons are what determines that element's reactivity. So let's talk a little bit now about what makes one element more reactive than another. So what makes, for example, sodium more reactive than magnesium? These are some really important key points here. One, all elements, and this is going to be a basic tenet for the next month pretty much, elements form bonds to get a full shell of outer electrons. That is why elements form bonds in the first place. They want to have a full shell and look like their nearest noble gas. Elements do this by losing, gaining, or sharing electrons with other elements. And the fewer electrons an atom has to lose or gain, the more reactive it is. So how many electrons did your sodium, your potassium, your lithium have, that first family?
How many?
How many valence electrons?
One.
Has one. So what does it need to do to look like its nearest noble gas? What does it need to do?
To complete the outer shell?
it needs to have a complete outer shell. How's it going to do that?
Like for example, sodium
Mm.
needs to have some bonding with chlorine to complete its outer shell, you know?
Yeah, right. Sodium would bond with chlorine to complete its outer shell. You'd form table salt. That's why students called me Mr. Knackle a lot last year. But what is happening? What's happening to that sodium atom when it makes that bond? How is it going to get a full shell? Those are your options. It's going to lose, gain, share. We're going to ignore share right now. It's not going to lose or gain.
bonding. Ionic bonding. Like they're sharing.
Yes, you're right. You're right. Yeah.
It's giving one of this
Oh, excellent. Most students there will say that it needs to gain 7, right? Most students there will say it needs to gain 7 electrons to have a full shell. They'll be like, it needs to gain 1, 2, 3, 4, 5, 6, 7. But atoms, I call them lazy. Really, it has more to do with electronic stability. If we tried to add 7 electrons, that's a lot of negatives. What do light charges do? They repel each other, right? They repel each other. So it's much easier, and elements, I'm going to say they're lazy, they will always take the least number of steps. So to look like its nearest noble gas, it will lose that 1 valence electron. Yeah?
If they're less than 4, they will lose, and if they're more than 4, they will gain.
Precisely. Precisely. Which is the next point I want to make. So if we look, for example, at, say, fluorine, fluorine will look like this, right? It's got 7 valence electrons, like all the other halogens do. What does fluorine need to do to look like its nearest noble gas?
Gain 1.
It needs to gain 1, right? If it gains 1 more electron, now it's happy, it's electronically stable, everything's hunky-dory. So let's explore the reactivity of elements then. What did I say in regards to what makes something reactive? If you read here, what makes something reactive? What makes something reactive?
The outer shell?
The fewer electrons an atom has to lose or gain, the more reactive that element is. So what do you think are the 2 most reactive families on your periodic table? Yep. Just take a stab at it. What do you think?
Halogens?
Excellent. Halogens is one of those groups. If we look here at the periodic table, how many electrons do your halogens need to gain or lose to get a full shell?
1.
That's right. They have 7 valence, so they need to gain 1. So let's say that bromine gains an electron. What does it look like now? Which noble gas does it have the same electron configuration as? If it gains 1 electron. If bromine gains 1, what does it look like now?
Krypton?
Excellent, it looks like krypton. So, since they only have to gain 1, they desperately will take that electron from somewhere. They are highly, highly reactive elements. What's the other most reactive group? They're also extremely reactive. For the same reason.
Alkali metals?
Excellent, your alkali metals. Why are they also super reactive?
They just need to lose one.
They just need to lose 1. Right? If we had potassium here, if it loses that electron, what electron configuration does it have now? What does it look like?
Argon?
Yeah, if it loses 1, it's going to look like argon, right? So the closer you are to looking like your nearest noble gas, the more reactive that element is, right? Your halogens will desperately try to gain 1. They'll react with just about anything. Your alkali metals desperately want to lose 1, right? They'll look like, they'll react with pretty much anything. So let's do a little example of that. I've actually brought with me some alkali metals here. And we're going to see that this sodium metal here is actually quite soft, quite malleable, but we store them in mineral oil. Randy, you may want to watch this. This is kind of neat. Now we store them in mineral oil. Why is that? Why don't we just store them in water? What did we learn about these alkali metals?
They're reactive.
Yeah, they are very, very reactive. In fact, they're so reactive, I'm going to use tongs to pick them up here. Because if I pick them up with my hand, well, it wouldn't end well. You're going to see right away. Now, sodium is one of the least reactive alkali metals. In fact, with the alkali metals, the further you go down, the more reactive they become. So what we see here is the sodium metal reacting with the water, and it's actually giving off hydrogen gas. If I had a match, I could actually light it on fire. I'm not going to get too close to it though, because it can blow up, which is pretty sad right now, to be honest. You can see it fizzling away though. So it's rapidly reacting with water. It's quite hot. It would scald me instantly if I touched it with my fingers. What do you think is going to happen when I put potassium in the water?
More reactive?
Yeah, it'll be more reactive. In fact, it is so reactive that it's very, very hot, the reaction. It'll auto-ignite. The hydrogen will start to burn. It forms like a fireball, and it'll actually blow up, which is kind of cool. So let's screw around with the potassium a little bit right now. Since we're not outside, I am going to use a fairly small chunk of it, however, because again, it will blow up. Now this one here, I'm going to stand a little further back from. Auto-ignites, and you see those little sparks? That's actually molten chunks of potassium flying off of it. Now, I'm going to have to wipe the counter down with water after this, because some of that actually went on the counter, and it's going to react and smoke when I actually wipe it up. I'm going to add now a little bit of this here. This is phenolphthalein. It is an acid-base indicator. And water would naturally make this go clear, right? There should be no change in color. Oh my god, there we go. There should be no change in color. However, what do we notice when I put that in there?
It turned purple.
Yeah, purplish pink, right? It turned very pink. What's actually happening here is the sodium metal and the potassium metal, as it reacted with the water, it produced hydrogen gas, and that's what you saw burning with the potassium, but it also produced sodium hydroxide, which is a drain cleaner, and it produced potassium hydroxide, both of which are bases. And we're going to learn all about acids and bases later on this year. So as you can see, those metals are very reactive. And let's now explore the reactivity of the other most reactive group there. But before I show that video, let's talk briefly about the second most reactive groups. What if we had, for example, actually I'm going to let you tell me, what do you think are the second most reactive families on the periodic table? Let's hear from someone else. What do you think?
Noble gases.
The noble gases are the least reactive group. Has anyone here ever heard of the Hindenburg? The Hindenburg was a dirigible, which is a rigid framed blimp, pretty much. And it was actually filled with hydrogen gas, the lightest of the elements. That's why they used it. It's super, super light. But hydrogen has a downside. We just learned that the alkali metals, that family, are they reactive? Oh yeah, right? So it ended horrifically. It blew up. And that's why we don't use hydrogen in balloons anymore. What do we use?
Helium.
Excellent. We use the second lightest element. We use helium. We use helium because the noble gases, do they already have a full shell of outer electrons? And look at your Bohr diagrams. Do they have a full shell? I see some nodding. They do, right? They do. Helium has a full shell at 2 valence electrons because your first shell can only hold 2 electrons. And then all of the rest have 8 valence, which is a full shell. So they don't really need to react with anything because they're already happy, right? They're already stable. So that's why we use helium, because it doesn't blow up. It's very stable. It doesn't react. So what do you think are the second most reactive families on that periodic table? So we established that the alkali metals and the halogens are the most reactive. What are the second most reactive families? Sorry?
Like chlorine and chlorine.
The halogens are I would say, are like one of the most reactive groups, right? With the alkali metals. What is the second most reactive groups?
Halogens.
Sorry?
Halogens.
The chalcogens, right? The chalcogens, the oxygen group. Because why? They have 6 valence and they only need what?
2 more.
They only need 2 more valence electrons to have a full shell. Right? If we look at oxygen here, oxygen only needs to gain 2 electrons to look like neon. So oxygen is extremely reactive, and we'll talk a lot more about it once we get into ecology. But what do you think is the other second most reactive group?
The alkaline metals.
Yes, the alkaline earth metals. Your beryllium, magnesium, calcium, strontium, barium. Why are they also the second most reactive family?
They need to lose 2.
They need to lose 2 electrons. Magnesium needs to lose 2, 1, 2 to look like neon, right? Calcium needs to lose 2 to look like argon, etc. Based on that same train of thought, what are the third most reactive families? We're just moving in here. What are the third most reactive families?
The nitrogen.
Yep. And?
Boron. No.
Yeah, no, you're right.
Okay, boron.
Yeah, so the nitrogen group and the boron group, because boron group, how many valence electrons does it have? 3, right? It needs to lose those 3 in order to get a full shell. Kind of lying to you a little bit here, but that's fine. And then the nitrogen group, how many valence electrons does it have?
5.
5, so it needs to gain 3 in order to have a full shell, right? Does that make sense? Perfect. Carbon group's a little weird. It traditionally doesn't really form ionic bonds all too well, which is the topic we're going to be talking about tomorrow. So we're not really going to focus too much on the electrons it loses and gains, because it actually likes to share more than anything. And these transition metals, the reason I didn't talk about them yet is because they're a little fickle. They don't necessarily always have the same number of valence electrons. They're called the multivalent metals for a reason. They can change the number of electrons that are in its outermost shell. So all of your transition metals and your heavier metals down here, with a few exceptions, can have differing numbers of valence electrons. Any questions at all? Alright, so let's explore now how reactive chlorine gas is.